Welcome to the Trackpads Military History Podcast, where we bring the terrain, the tactics, and the stories of soldiers to life. Each episode goes deeper than the written article, giving you a front-row seat to the battles that shaped history. Discover more at trackpads.com.
The first military balloon rose into the skies above Fleurus in 1794, and the soldiers who steadied its lines on the ground looked upward in awe and disbelief. For the first time in modern battle, an army had gained a vertical advantage. Observers in the swaying basket reported enemy movements as if from the hand of God, sketching maps and shouting down corrections that commanders could scarcely believe. It was a fragile contraption cloth, gas, and rope, but it revealed something profound. If men could see the battlefield from above without risking a cavalry patrol, the very rhythm of war might change. In that moment, soldiers glimpsed a future where height and perspective mattered as much as muskets and bayonets. More than a century later, across an open field in Ohio, a new experiment rattled into motion. Engineers stood around a wooden contraption balanced on a rail, its engine coughing to life with a harsh staccato. Called the Kettering Bug, it promised something almost unthinkable. A pilotless airplane that could fly by itself toward a target and crash with explosive effect. The device was ungainly, its wings fragile, its guidance system a patchwork of gyroscopes and mechanical counters. But when it lifted into the air, buzzing like some enormous insect, those watching felt the same uncanny sense of possibility that French soldiers had felt long before. Once again, the battlefield seemed on the verge of transformation. These two images, the balloon over Belgium and the bug over Dayton, frame a story of persistence and imagination. For centuries, armies have sought ways to extend their reach without sacrificing men to the risks of exposure or the perils of flight. The tools may have changed from hydrogen to wood and later to silicon, but the impulse has always been the same: to see farther, strike harder, and protect the living through machines. Each generation of innovation carried its own awe and its own doubts. Could a balloon survive a storm? Could a bug find its target? And in later years, could a radio-controlled drone stay on course against interference? The story of drones before drones is not only technical, but deeply human. It is the story of soldiers learning to trust fragile contraptions, of commanders weighing novel tools against proven traditions, and of engineers pressing the limits of what cloth, wire, and imagination could achieve. Today's unmanned aerial systems may be sleek, precise, and digital, but they trace their ancestry to those early, wavering steps into the sky. The legacy of balloons and bugs is the recognition that war has always been about vision and reach, and that every new machine is simply another way of extending the soldier's grasp. The revolutionary armies of France were the first to discover what a balloon could truly do for battlefield vision. At Fleurus in 1794, the French launched l'Entreprenant, a hydrogen-filled aerostat tethered high above the rolling fields where Austrian and Dutch troops maneuvered. From its basket, officers and trained observers could watch entire brigades shift positions in near real time, noting formations and movements invisible to cavalry scouts below. Orders, once delayed by couriers or subject to guesswork, could now be drafted with fresher intelligence than ever before, reshaping the tempo of command. Soldiers in the ranks looked up at the looming gas bag as both reassurance and spectacle, while enemy troops viewed it with dread. For generals, it marked a startling evolution, the first inkling that vertical observation could become as decisive as cavalry charges or artillery fire, not through brute strength but through perspective. Yet every advantage was bound by tangible weaknesses. Balloons demanded enormous amounts of hydrogen, generated in cumbersome field laboratories that required wagons of sulfuric acid, iron filings, and water. The equipment creaked under its own complexity, forcing commanders to carefully plan launches around the geography of their campaign. Roads needed to be secure for heavy wagons, open fields chosen free of trees and obstacles, and weather calm enough to make the ascent worthwhile. A sudden squall could undo hours of preparation, dragging the balloon across hedgerows or snapping ropes under strain. Soldiers assigned to balloon duties often found themselves working less like fighters and more like engineers, hauling lines, tending to volatile chemicals, and balancing the safety of their comrades against the capriciousness of wind. This dependency revealed how fragile innovation could be when pressed into the dirt and mud of real campaigns, where nature often proved as hostile as the enemy. The human experience of those flights was as defining as the tactical benefits. Observers, suspended in wicker baskets, described sensations of both awe and dread. Hanging hundreds of feet above the clash of muskets and artillery, they found themselves both isolated and exposed, able to see the whole battlefield, yet acutely aware of their vulnerability. A single well-aimed shot or a lucky gust might turn their perch into a death trap. Reports often mingled precise battlefield notes with admissions of nausea, vertigo, and an eerie sense of detachment as they floated in the relative quiet above the roar of battle. On the ground, soldiers learned to see the balloon as a symbol of modernity, a harbinger that war was entering a new era, but also as a liability. Enemy gunners made the balloon a priority target, sharpshooters waited for the chance to puncture its envelope, and cavalry raiders tried to seize the gas wagons. The balloon altered tactics, but it never freed armies from the hazards of combat. Still, the lesson endured in military memory. For the first time, commanders recognized that vantage from above could rewrite the terms of reconnaissance, in ways scouts on horseback never could. A balloon might drift or falter, but when it succeeded, it offered something generals long craved: certainty in a world of guesswork. That certainty, however fragile, proved powerful enough to reshape doctrine. Traditional methods of scouting could be blocked by terrain or ambushed by enemy screens, but balloons soared over obstacles and surveyed valleys or river crossings in one sweeping gaze. Even with limitations, their presence gave armies confidence to maneuver with fewer blind spots. European militaries took notice, and in the decades that followed, the balloon moved from oddity to prototype. It was not the solution to warfare, but it was the first chapter in a longer lineage of machines built to give soldiers eyes where no human could safely go. During the American Civil War, the fragile promise of aerial observation returned in the form of Professor Thaddeus Lowe's Balloon Corps. And with it came a glimpse of how modern communication could reshape combat. Lowe convinced President Lincoln and senior generals that his tethered balloons could provide real-time intelligence, not just sketch maps delivered after long delays. From his baskets, telegraph wires stretched back to Union artillery, allowing gunners to receive immediate corrections, 50 yards left, increase elevation, that transformed shelling from a guessing game into a deadly science. For Confederate soldiers suddenly pinned down by fire adjusted from the sky, the sensation was eerie and demoralizing. Their adversaries seemed to possess an eye in the heavens, one that stripped away the protection of smoke, trees, or cover. For Union soldiers, the balloon became a symbol of ingenuity, though many regarded it with the same mixture of curiosity and unease as their French forebears had decades earlier. The logistics of Civil War balloons were demanding. Hydrogen still required portable laboratories of acid, iron, and water transported by mule and wagon to forward positions. Winches and heavy ropes had to be secured in open fields where artillery could easily spot them. Wind became an unrelenting enemy, often jerking baskets violently or dragging balloons across treetops. Crews trained to haul and stabilize the aerostats became specialists in a new craft, more like sailors than soldiers, manning lines under fire and tending to hissing gas generators while shells burst nearby. Terrain dictated everything. Rolling hills might block sight lines, while forests concealed entire divisions beyond an observer's view. Each launch was a gamble against weather, visibility, and enemy guns, with the payoff measured in whether a general could trust the reports coming down the telegraph line. For the men in the baskets, the psychological strain was intense. Perched in fragile wicker gondolas with nothing between them and enemy sharpshooters, observers reported a constant awareness of their vulnerability. A single bullet might rip fabric, causing a slow and terrifying descent, or worse, a sudden uncontrolled drift into hostile territory. Many accounts described the sensation of being simultaneously omniscient and helpless, able to see the entire flow of battle, yet powerless to shield oneself from danger. Some found the experience exhilarating, a chance to participate in war from a godlike perspective. Others dreaded each ascent, aware that enemy marksmen and artillery crews watched for the moment the balloon lifted into view. This strange blend of empowerment and exposure defined the observer's experience, one that echoed through later generations of aerial reconnaissance. Not every Union general welcomed the balloons. Some considered them a novelty or distrusted Lowe's reports, preferring cavalry scouts who could fight if needed and return with written intelligence. The Balloon Corps also suffered from bureaucratic disputes, funding struggles, and clashes between Lowe and commanders who resisted the disruption of their routines. Yet even with these limitations, the idea of live aerial observation had proven itself. Union artillery became sharper, Confederate positions more vulnerable, and the very concept of scouting was transformed. The balloons did not win the war, but they showed what the future might hold. A battlefield where vertical vision could mean the difference between blundering blindly and striking with precision. For the first time, the United States had embraced aerial reconnaissance, and though the technology would fade after the war, the concept had taken root deeply enough that it would return in the conflicts of the 20th century. The First World War took the lessons of earlier balloon experiments and turned them into a fully integrated system of warfare. By 1914, the static nature of trench fighting and the dominance of artillery demanded better ways to spot and direct fire, and kite balloons became a fixture along the Western Front. Unlike the rounded gas bags of earlier decades, these were elongated, sausage-shaped aerostats stabilized by fins, designed to ride the wind with greater steadiness. They hovered above divisional sectors, tethered by steel cables, with observers dangling in baskets equipped with telephones. From their elevated perch, these men could call down precise coordinates, linking what they saw through binoculars to artillery maps on the ground. The balloon was no longer a fragile curiosity. It had become an indispensable node in a lethal kill chain that made trench lines even deadlier. That kill chain operated with ruthless efficiency. Observers scanned for enemy troop movements, new batteries being dug in, or supply convoys snaking along rear roads. When a sighting was made, it was relayed down the tethered phone line to artillery commanders, who plotted it on trench maps using standardized grid references. Batteries shifted fire within minutes, sending shells screaming across no man's land to rain down on exposed targets. The speed of this loop astonished soldiers on both sides. Positions that once offered relative safety-sunken lanes, hidden valleys, or even the cover of night were suddenly vulnerable. The balloon's watchful gaze pierced the battlefield, and artillery became not just an area weapon but a tool of near-precision destruction, guided from the sky. The power of balloons made them prized targets, and balloon busting became a dangerous specialty for fighter pilots. Attacking one meant braving concentric rings of defenses, anti-aircraft guns, machine gun nests, and patrolling fighters circling to intercept. Pilots dove through sheets of tracer fire, spraying incendiary ammunition into the balloon's hydrogen envelope, often igniting it in a spectacular blaze. For observers, this was the moment of greatest peril. Parachutes became standard, and countless men bailed out in desperate leaps as their balloons collapsed in flaming wreckage behind them. Heroes and aces built reputations on these missions. Frank Luke for the Americans, Willie Coppens for the Belgians. But the casualty rate was grim. Each balloon destroyed was a victory celebrated by infantry, who knew how much misery those sausages could bring. Even without enemy fighters, nature itself tested balloon operations. The Western Front was a landscape of smoke, fog, and shifting weather. Heavy shell fire often filled the air with dust and haze, obscuring the ground below. Low-hanging clouds limited altitude, while rain turned baskets into swaying, miserable perches. Observers strained to distinguish between a moving column and a tree line shivering in the wind. Terrain dictated coverage. Ridgelines and forests could conceal entire formations, forcing balloons to be moved constantly for better vantage points. Ground crews, often under fire themselves, manned winches and hydrogen generators, hauling the balloon down at the first sign of an enemy raid or storm. Their labor was unending, their risk constant, as they worked to keep the aerial link alive between sky and guns. Leadership and organization gave the kite balloon system its edge. Observer teams operated with drilled precision, one scanning with binoculars, while another relayed corrections over the phone. On the ground, artillery staffs learned to trust and act quickly on balloon reports, shifting batteries mid-barrage to exploit sudden opportunities. The tempo of operations quickened, with commanders able to mass fire or counter-battery enemy guns faster than ever before. This integration transformed artillery from a blunt instrument into a responsive weapon system, reshaping how armies attacked and defended. The kite balloon may have seemed ungainly, but in its cables and telephone lines lay the prototype of modern networked warfare. It bound together observation, communication, and firepower into a system that made the Great War's artillery duels the deadliest the world had yet seen. The closing years of the First World War saw militaries searching desperately for ways to break stalemate and deliver decisive strikes, and in the United States that urgency produced one of the most remarkable inventions of the era: the Kettering Bug. Conceived by Charles Kettering and his team of engineers, this wooden and canvas contraption looked like a stripped-down airplane balanced precariously on a launch rail. What set it apart was the absence of a pilot. Instead, the Bug relied on a crude autopilot system that used Sperry gyroscopes, a barometric altimeter, and a mechanical revolution counter that measured propeller turns to estimate distance flown. When the counter reached its preset number, the engine shut off, and the Bug nosed into a dive with a 180-pound explosive payload. For soldiers and observers at testing grounds in Ohio, the sight of this automatic airplane was unsettling and awe-inspiring. A wooden machine buzzing into the sky without a human hand at the controls. The mechanics of operating the Bug revealed just how fragile early autonomy could be. Launch required a team of ground crewmen to prepare rails, adjust the gyroscopic stabilizers, and set the revolution counter for the intended range. Once released, the craft rattled forward, gathering speed until it lifted with a shudder into the air. For those watching below, it often wobbled uncertainly, buffeted by winds it could not anticipate or correct against with finesse. Sometimes it managed to track straight, buzzing toward the horizon. Other times a gust caught it broadside, sending it veering off course or crashing prematurely. Engineers noted how small variations in terrain and weather produced massive differences in performance. Yet every successful flight proved the concept. A pilotless craft could, in fact, be guided to a distant point and used as a weapon. The Army envisioned the Bug as a strategic, deep-strike tool capable of bypassing trenches and hitting depots, railway junctions, or massed reserves without risking pilots. The idea was bold, perhaps decades ahead of its time, but it collided with the hard realities of technology. Navigation drift was severe, reliability was poor, and controlling consistency across multiple flights proved elusive. In a battlefield where weather shifted hourly and terrain offered little forgiveness, commanders doubted whether such a device could be counted on. Before answers could be found, the armistice of November 1918 arrived, halting further trials and shelving the project. Kettering's invention became a historical footnote, a weapon that never entered combat but tantalized military thinkers with its possibilities. The dream of replacing manned bombers with expendable machines would have to wait for sturdier engines, better navigation, and a doctrine willing to embrace them. Even so, the Bug's legacy was unmistakable. Its gyroscopic controls fed directly into the development of later autopilots. The mechanical revolution counter foreshadowed the inertial navigation and programmed flight paths of cruise missiles. And its expendable nature introduced the concept of attritable airframes machines cheap enough to risk yet capable enough to matter. Just as importantly, it forced soldiers, engineers, and commanders alike to grapple with a new set of questions. Could they trust a weapon that flew itself? Could it deliver the same precision and reliability as a human pilot? Would reliance on such devices change the very calculus of courage and sacrifice in war? Though the Kettering Bug never struck German lines, it had already struck the imagination, planting seeds that would germinate decades later in the drone arsenals of a new century. Between the wars, the dream of pilotless flight survived not as a weapon, but as a training tool. Britain led the way with its Queen Bee, a radio-controlled biplane introduced in the 1930s to give anti-aircraft gunners moving, realistic targets. The name itself, playful yet fitting, would echo down the decades as drone, forever linking unmanned aircraft to the buzzing sound of a bee in flight. For British gunners who had previously practiced against towed sleeves or stationary dummies, the challenge of tracking and firing at a darting aircraft sharpened their skills immeasurably. The Queen Bee demonstrated that expendable machines could save lives in training and, indirectly, in combat. It also cemented the principle that unmanned flight did not need to prove itself in battle to have value. It could quietly become part of the daily routine of soldiers preparing for war. The United States soon adopted the idea, thanks in part to the efforts of Reginald Denny, a Hollywood actor turned aviation enthusiast. Denny's radioplane company produced thousands of small, twin-boomed drones that became the backbone of American gunnery training in the late 1930s and 1940s. These aircraft were rugged, relatively cheap, and designed to be shot down. On training ranges, anti-aircraft crews braced for the challenge of hitting something that moved and maneuvered like a real enemy plane. The crack of shells, the streaks of tracers, and the satisfaction of watching a radioplane tumble in smoke and debris gave soldiers confidence that they could do the same to enemy bombers. For the first time, the military treated drones not as oddities but as consumables tools to be produced, used, and destroyed in quantity. The technology, however, revealed its limitations. Radioplanes and their British cousins depended on line-of-sight radio control, meaning they could not venture far from operators. Control signals could be lost or distorted by terrain, interference, or even the quirks of radio propagation on a humid day. Failures were common. Drones spun into the ground, veered wildly out of range, or, on occasion, vanished over the horizon never to be recovered. To make the system work, militaries developed intricate choreography. Often, a manned aircraft would escort the drone into the target area, handing off control to ground operators who guided it into firing lanes. These exercises became as much about teamwork between manned and unmanned aircraft as they were about gunnery practice. In those moments, the outlines of future Doctrine's piloted aircraft directing drones were faintly visible. The radioplane factories themselves became symbols of industrial mobilization. In Southern California, assembly lines produced thousands of drones, staffed by young workers, many of them women filling roles vacated by men in uniform. Among them was a woman named Norma Jean Mortensen, later known to the world as Marilyn Monroe, discovered during a photo shoot at the plant. Her story, often retold, underscored how deeply drones had seeped into the fabric of wartime society. They were no longer rare inventions handled by eccentric engineers. They were everyday products, assembled like rifles or helmets, destined for gunnery ranges rather than battlefields. This mass production showed that drones had found their place, not yet as offensive weapons, but as expendable tools that trained men for the skies to come. The interwar and early World War II years proved something profound. Even when technology limited range and reliability, unmanned aircraft could serve vital purposes. They built competence, saved pilots for real missions, and forced gunners to engage targets that fought back, if only in practice. By the time global conflict erupted in 1939, militaries on both sides had integrated drones into their training culture. These were not the drones of modern combat, but their significance lay in acceptance. For the first time, soldiers and commanders alike assumed drones had a permanent place in military life. They were no longer questions of if or why, but of how many and how soon. That mindset laid the groundwork for the leap from training tools to combat weapons in the crucible of World War II. World War II and the Cold War saw the evolution of unmanned weapons, from crude glide bombs into sophisticated reconnaissance drones, and that sweep reads like a lesson in ambition colliding with countermeasures. Germany first turned pilotless guidance into lethal practice with weapons such as the HS-293 and the Fritz X radio-steered glide bombs launched from bombers to strike ships and harden targets. Operators watched and guided these weapons by line-of-sight radio, correcting their flight as they fell toward targets. The effect on Allied convoys was immediate and terrifying. Sailors learned quickly that these were not the dumb bombs of old but guided missiles that could be steered around evasive maneuvers. The response was equally swift: jamming, aggressive maneuvering, layered anti-aircraft barrages, and tactical changes to formation and escort doctrine. The duel became emblematic of a new truth. Any gain in reach invited an immediate and costly adaptation from the defender. The glide bomb era exposed the brutal arithmetic of emissions and defenses. Every radio signal that let an operator steer a weapon also gave the enemy something to jam or home in on. Allied jamming and evasive tactics blunted many attacks, demonstrating that guidance without secure, robust links was a brittle advantage. Yet those early systems proved an idea: that a weapon could be guided remotely to increase accuracy and lessen the need for piloted, attritable sorties. At the same time, the human workload shifted. Instead of a pilot wrestling controls in the cockpit, now an operator somewhere else, sometimes in the launching bomber, had to manage guidance, watch the fall, and react to countermeasures. The mental strain of that task, especially while under fire or in cramped control stations, became part of the unmanned cost that technology did not erase. American experiments followed, and some approached what we would now call remote piloting. The Navy's TDR-1 project fitted assault drones with television cameras that transmitted live images back to a control aircraft. An operator would guide the drone toward a target by watching a small, grainy screen. In the broken geography of Pacific Islands, reefs, jungle, and coral atolls, this capability promised precision strikes against pillboxes and supply points that were dangerous for manned aircraft to attack directly. In practice, the TDR crews faced severe constraints, line-of-sight limits, interference from atmospheric conditions, and the ever-present risk of enemy fighters. Still, those missions were a proof of concept. A human could fly a weapon from afar using visual feedback, and in some cases, that method delivered results that would have been hard to achieve otherwise. Not all wartime attempts succeeded, and some turned tragic. Operation Aphrodite converted aging B-17s and B-24s into massive radio-controlled flying bombs packed with explosives, crews taking off manually and then bailing out while a chase plane attempted to guide the aircraft to its objective. The missions were plagued by mechanical failure, radio problems, and horrifying accidents. Several volunteers died during testing and combat sorties. Germany's own Mistel composite aircraft fighters mounted atop explosive-laden bombers had limited operational effect and exposed how difficult it is to marry crude guidance with the chaos of combat. These failures taught a bitter lesson. Raw, destructive potential meant little without reliable guidance, survivable command links, and doctrines that protected both crews and the systems they used. When strike concepts proved precarious, reconnaissance became the domain where unmanned systems truly flourished. The Cold War pushed the United States and its allies to seek eyes where pilots could not safely fly. The Ryan Firebee began life as a target drone but evolved into the Lightning Bug, a reconnaissance platform that flew pre-programmed routes over Vietnam, China, and other sensitive areas. These expendable drones carried cameras and sensors, returning film cartridges for recovery, sometimes caught midair by recovery aircraft or plucked from the sea. Field crews learned to chase and retrieve these machines, and operations required complex choreography, launch crews, recovery teams, and analysts ready to exploit the images. The value was enormous intelligence that would have cost pilots lives or provoked incidents now arrived with the rub of sand and oil, a little worse for wear but invaluable for planners. Recovery and resilience became defining features of Cold War drone operations. Mid-air captures, where a recovery plane snagged a parachuting film canister or clipped a descending drone reed like circus acts, requiring timing, skill, and stubborn crews. When retrieval failed, the sea became a hungry grave. Salvage teams raced to recover frames, cameras, and film before currents or enemy patrols claimed them. At the same time, air defenses matured. Radar networks, surface-to-air missiles, and electronic warfare increasingly threatened drone corridors. The move toward higher speed and altitude exemplified by projects like the ramjet-powered Lockheed D-21 was driven by the desire to outrun defenses. The D-21, launched from modified carriers or B-52s and intended to photograph denied territory at several times the speed of sound, proved expensive and accident-prone, but it showed how far engineers would go to preserve reconnaissance capability. Across World War II and the Cold War, two consistent themes emerge. Unmanned systems offer the promise of reach and reduced human risk, but they also demanded new forms of logistics, human skill, and doctrinal adaptation. Operators, recovery crews, and analysts formed an ecosystem around machines that were, by design, expendable, yet operationally precious. Every technical advance, better radios, TV feeds, ramjets, came with a counterforce in jamming, interception, and retrieval difficulty. The net result was a steady professionalization of unmanned operations. What began as improvisation matured into units, procedures, and cultures that treated drones as integral tools of war. By the time the Cold War reached its high tension, unmanned aerial systems were no longer curiosities. They were indispensable instruments in the contest of intelligence, strike, and technological one-upmanship. From the windswept fields of revolutionary France to the high-speed experiments of the Cold War, the lineage of drones reveals a persistent truth. Militaries have always sought to see farther and strike harder without exposing their people to unnecessary risk. Each era produced its own fragile but groundbreaking answers. Balloons filled with volatile gas, wooden bugs that buzzed toward their targets on preset courses, radio-controlled targets that danced across gunnery ranges, and jet-powered reconnaissance drones that skimmed hostile skies. None were perfect. All were limited by the physics of wind, the flaws of machinery, and the resistance of skeptical commanders. Yet each machine left an imprint, moving the idea of unmanned flight from improbable novelty to accepted reality. The common threads across centuries are striking. Weather and terrain remained as much adversaries as enemy soldiers. Operators and observers lived with exposure and uncertainty, whether swaying in wicker baskets or hunched over flickering TV screens. Commanders wrestled with trust. How much faith could be placed in a device when lives and missions depended on it? And every success provoked a countermeasure. Jamming, interception, camouflage, or simply the chaos of combat that no autopilot could predict. These patterns remind us that technology alone never transforms war. It is the fusion of machine, doctrine, and human judgment that creates lasting change. Perhaps most important is the human factor, which endures despite the promise of automation. The soldiers who studied balloon ropes, the crews who launched bugs on rails, the gunners who learned to aim at drones, and the technicians who recovered battered Firebees all shared the same experience of adapting to a new kind of warfare. For them, drones were not abstract ideas but tangible machines, noisy, fragile, and unpredictable. Their labor, courage, and frustration kept those machines flying, proving that even in the age of unmanned systems, war remained deeply human. Today's sleek, satellite-linked UAS inherit more than a technical lineage. They inherit these dilemmas and lessons. Modern operators still balance reach with reliability, still face electronic countermeasures, and still grapple with how much autonomy a machine should wield. When we look back at balloons, bugs, and lightning bugs, we see not primitive ancestors but direct precursors, each generation solving one problem while leaving another for the future. The story of drones before drones is a reminder that warfare's evolution is continuous, shaped by both ingenuity and imperfection. Each machine, whether floating, buzzing, or streaking at supersonic speed, extends the soldier's vision and reach, but never removes the soldier's burden of judgment.
Thank you for joining us on the Trackpads Military History Podcast. If you enjoyed this deep dive into the battlefield, be sure to explore more articles, episodes, and series at trackpads.com.